There was a time when human beings thought fire was alive. They believed it was a spirit that ate wood and breathed light. Even today, if you stare long enough at a flame, it feels alive, it dances, it flickers, it reacts, it makes sound, it changes color, it grows, it dies. The question feels simple, but it hides something deeper than most people realize. Why does fire burn? Not why is it hot, not why is it bright, but why does it burn at all? Why does matter suddenly transform into heat and light when it meets oxygen? Why does wood become flame and then vanish into ash, an invisible gas? If you ask most people, they would say combustion. They would say chemical reaction. They would say oxidation. But if you had asked Richard Feynman, he would have smiled in that slightly mischievous way and said something else. He would have said that you are not really asking about fire. You are asking why nature prefers certain arrangements of atoms over others. And once you understand that, fire stops being magic and starts becoming something much stranger. To understand why fire burns, we need to step backward before fire existed on Earth. Long before trees, long before air, long before oxygen filled the sky. We need to go back to the birth of atoms themselves, because fire is not something added to matter. Fire is something hidden inside matter from the very beginning. Every piece of wood contains atoms bonded together in specific patterns. Those bonds are not just connections, they are energies stored in electric fields between positively charged nuclei and negatively charged electrons. Matter is held together by electromagnetic forces. When two atoms bond, they settle into a state that balances attraction and repulsion. That balance is not random. It obeys quantum rules. The electrons do not orbit like planets. They exist as probability clouds. They form orbitals that determine how atoms connect. When carbon bonds with hydrogen and oxygen and wood, it forms molecules that are stable but not perfectly stable. They are in what physicists call a metastable state. That means there exists another arrangement of atoms that is more energetically favorable, more stable. Fire is what happens when matter finds the path to that more stable configuration. Oxygen is a greedy atom. It has 6 electrons in its outer shell, and it wants 8. That desire is not emotional. It is quantum mechanical. Atoms tend toward configurations that minimize energy. When oxygen encounters carbon and hydrogen and wood at high enough temperature, the molecules break apart, bonds snap. Not because they want to, but because thermal motion shakes them violently. Heat increases kinetic energy. The atoms vibrate harder. At a certain point, the bonds can no longer hold. Once they break, new bonds can form. Carbon bonds with oxygen to form carbon dioxide, hydrogen bonds with oxygen to form water vapor. And here is the crucial part, that new bonds are stronger than the old ones. When stronger bonds form, they release excess energy. That released energy appears as heat and light. That is fire. But that explanation hides something profound. Why are the new bonds stronger? Why does the universe prefer carbon dioxide and water over cellulose and lignin? The answer lies in quantum electrodynamics, the theory Feynman helped build. At the microscopic level, atoms interact by exchanging photons. Not the light we see, but virtual photons. These exchanges create forces. The energy of a molecule is determined by the arrangement of electrons and how they share those exchanges. When carbon and oxygen bind, their electron clouds overlap in a way that lowers the total electromagnetic match of the system. Nature prefers lower energy states. It always rolls downhill in energy space. Fire is matter rolling downhill. The flame is simply the visible trace of that descent. Most people think of heat as something added. But in combustion, heat is not added. It is released. The system starts in a higher energy configuration and transitions to a lower one. The difference does not disappear. Energy cannot vanish. It transforms. Some of it becomes kinetic motion of molecules. That motion is temperature. Some of it excites electrons into higher quantum states. When those electrons fall back down, they emit photons. That emission is light. The yellow color of a candle flame comes largely from tiny soot particles heated to incandescence. The blue part comes from excited molecular transitions, especially from CH radicals. Every color is a quantum signature. Every flicker is statistics. Feynman often insisted that when you ask why something happens, you must clarify the level of explanation you want. If you ask why fire burns, do you want chemistry? Do you want electromagnetism? Do you want quantum field theory? Or do you want thermodynamics? Each answer is true in its own language. Thermodynamics says reactions proceed in the direction that increases entropy. When wood burns, solid structured carbon chains become gas molecules spreading outward. Order becomes disorder. Entropy increases, That statistical preference drives the reaction. Chemistry says oxidation releases energy because bond energies differ. Electromagnetism says electric charges rearrange to minimize potential energy. Quantum mechanics says wave functions overlap into lower eigenstates. These are not separate answers. They are translations of the same underlying story. The reason fire feels destructive is because we are creatures of structure. Wood feels solid. It has shape. But at the atomic level, wood is mostly empty space. Its atoms are arranged in repeating polymers. Fire breaks those polymers apart. It does not destroy atoms. It rearranges them. Destruction is a human word for reconfiguration. Matter does not disappear in flames. It transforms into gas and ash. The mass remains. Carried away as invisible carbon dioxide and water vapor. Even the brightness of flame is not matter burning away. It is energy being released as new bonds form. There is something almost unsettling about this realization. The flame is not a thing. It is a process. It is not a substance you can hold. It is a region of ongoing chemical reactions. The shape of a flame is determined by fluid dynamics and buoyancy. Hot gases rise because they are less dense. Fresh oxygen flows in from below. The flame stabilizes into a teardrop shape in normal gravity. In microgravity, flames become spherical. They no longer stretch upward because there is no buoyant flow. On the International Space Station, astronauts have watched flames form quiet blue spheres. This alone should change how you think about fire. Even its shape is not fundamental. It is a conversation between gravity and chemistry. But Feynman's deeper point is even more radical. Fire is not special. Everything around you is trying to burn in some sense. Not necessarily with visible flame, but matter constantly seeks lower energy states. Iron rusts. That is slow burning. Metabolism in your body is controlled combustion. Glucose reacts with oxygen to release energy gradually, rather than explosively. If all your metabolic reactions happened at once, you would explode with heat. Life has found a way to step down energy slopes slowly. Fire is just the fast version. If you trace this slope far enough back, you reach the stars. The oxygen that feeds flames was forged in stellar interiors. Carbon, too. Inside stars, nuclear fusion creates heavier elements. Those elements spread through space when stars explode. Planets form. Life evolves. Eventually, wood grows, storing solar energy captured through photosynthesis. When you light a match, you release sunlight trapped in chemical bonds millions of years ago. Fire is ancient starlight returning to radiation. The flame is a memory of a star. And yet none of this answers the haunting part of the question. Why does the universe permit such rearrangements? Why are there energy gradients at all? Why does entropy increase? Feynman would caution against asking why in a metaphysical sense. Physics does not answer why the laws are what they are. It describes how they operate. Fire burns because electrons obey quantum mechanics, because the electromagnetic force has a certain strength, because carbon and oxygen have certain energy levels. If those constants were different, flames might not exist. Chemistry might not exist. We might not exist. So when you look at a flame, you are looking at quantum electrodynamics in action. You are watching trillions of atoms break old partnerships and form new ones. You are seeing the electromagnetic field reshaping matter into a lower energy configuration. You are seeing entropy rise. You are seeing gravity sculpt hot gases upward. You are seeing sunlight liberated from chemical bonds. Fire is not a primitive element. It is the visible signature of deeper laws. This realization destroys a comfortable illusion. We tend to think the world is made of things, solid objects with identities. But fire reveals that everything is process. Wood is process, air is process, even your own body is continuous chemical reaction. Stability is temporary balance. The universe is not static. It is perpetually seeking arrangements that lower energy and increase entropy. Fire is simply one dramatic way that seeking becomes visible. If you ask again why fire burns, the simplest truthful answer is this: because matter prefers other shapes, because electrons find a configuration that costs less energy, because the electrons find a configuration that costs less energy, because once begun, the reaction sustains itself by releasing enough energy to break more bonds. The flame feeds on its own liberation of energy. It is self-propagating until fuel or oxygen runs out. When either is gone, the descent stops. The system has reached local stability. In part 2, we will go even deeper. We will leave chemistry and explore the quantum roots of temperature, the statistical origin of entropy, and why the arrow of time itself is hidden in every flame. Because the real shock is not that fire burns. The real shock is that burning reveals which direction time flows.
The furrow hidden inside the flame.
In part 1, we stripped fire of its mystical identity and saw it as a rearrangement of atoms rolling downhill in energy space. But that explanation hides something even more unsettling. Fire does not just release heat. It reveals the direction of time. A flame never unburns itself. Smoke does not gather from the air and quietly rebuild a log. Ash does not leap back into wood. Something about combustion draws a line between past and future. That line is not written in the equations of basic mechanics. If you look at Newton's laws or even Schrodinger's equation, you will find something disturbing. That they work the same forward and backward. The mathematics does not prefer a direction of time, yet when you light a match, everyone knows which way events will unfold. So why does fire burn only forward? Richard Feynman loved this tension. He pointed out that at the fundamental level, physical laws are mostly time symmetric. If you filmed 2 billiard balls colliding and played it backward, the motion would still obey Newton's equations. If you filmed 2 atoms exchanging momentum, the reversed film would still satisfy quantum mechanics. But if you film a log burning and reverse the footage, the illusion collapses. We immediately know something is wrong. The reversed flame looks absurd because macroscopic processes obey thermodynamics. And thermodynamics introduces something not obvious in microscopic rules: probability. To understand the arrow of time inside fire, we need to understand entropy. Entropy is often described as disorder, but that word is too vague. Entropy is the measure of how many microscopic arrangements correspond to a macroscopic state. A log is highly structured. Its carbon atoms are arranged in long repeating polymers. Its molecules are organized into cellulose fibers. It is a low entropy configuration because there are relatively few ways to arrange atoms that still look like a solid log. When it burns, those atoms become gases that spread outward. Carbon dioxide molecules fly freely. Water vapor diffuses into the air. There are astronomically more ways to arrange those gas molecules than to assemble them into a tree trunk. The second law of thermodynamics states that in an isolated system, entropy tends to increase, not because it must in a strict mechanical sense, but because higher entropy states are overwhelmingly more probable. Imagine all possible microscopic arrangements of atoms in a room. Only a tiny fraction correspond to a neat ordered configuration like an intact log. Almost all correspond to dispersed gas and ash. When combustion begins, the system moves toward the far more numerous high entropy configurations. It is not that nature forbids reverse burning, it is that the odds against it are unimaginably large. Feynman once explained this using a simple but devastating idea. Suppose you release a drop of ink into water, the ink spreads out. If you watch the molecules individually, nothing in their microscopic equations prevents them from spontaneously regrouping into a drop again. But the probability is so small that you will never see it happen in the lifetime of the universe. Fire is the same story told with heat and light. Once the energy disperses into trillions of moving molecules and photons, the chance that all of them reconvene in exactly the right positions and velocities to rebuild the wood is effectively zero. The future differs from the past because probability favors dispersion. This has profound implications. When you light a flame, you are not watching a violation of time symmetry at the microscopic level. You are watching statistics dominate. Temperature itself is statistical. It is not a property of one molecule. A single molecule does not have temperature. Temperature describes the average kinetic energy of enormous numbers of molecules. In fire, chemical reactions release energy that increases molecular motion. That motion spreads through collisions, distributing energy outward. The flame is a region where average kinetic energies are higher. As molecules collide, energy randomizes. Order dissolves into motion. But what about the light? The glow of fire seems directional. Photons stream outward from the flame. If time were reversed, photons would converge precisely into the same spot, reassembling excited atoms in perfect synchrony. That is not impossible according to quantum electrodynamics. Feynman's own formulation of QED treats interactions as sums over all possible paths. The equations allow photons to be absorbed and emitted symmetrically in time. Yet again, probability rules. The coordinated convergence of trillions of photons into just the right quantum states to reconstruct a burning log is so improbable that it is never observed. The arrow of time hidden in fire is therefore not written in electromagnetism itself. It is written in the initial conditions of the universe. Our cosmos began in an extraordinarily low entropy state. That fact alone drives every flame that has ever existed. Because the early universe was highly ordered, there has been room for entropy to increase ever since. Stars formed, heavy elements formed, planets formed, chemical energy accumulated in molecular bonds. Fire is one of countless processes that release that stored potential as the universe drifts toward thermodynamic equilibrium. Equilibrium is the silent destination of all flames. When a fire burns out, the system reaches a state where no further favorable reactions can occur. The fuel is exhausted, oxygen may be depleted, the chemical energy gradient has flattened. The system has settled into a higher entropy configuration. If you waited unimaginably long, even the heat from the ashes would radiate away, dispersing into space. Eventually, everything tends toward thermal uniformity, a state where no energy gradients remain to drive further processes. No gradients means no flames, no work, no structure. But we do not live in equilibrium. We live in a universe full of gradients. The sun is hotter than Earth. Earth's interior is hotter than its surface. Chemical bonds store differences in potential energy. Life itself depends on gradients. In your cells, mitochondria create energy differences across membranes. These differences allow chemical work to proceed. You are, in a sense, a carefully controlled flame. Glucose reacts with oxygen, step by step releasing energy that powers your body. Without those reactions, there is no metabolism. Without controlled burning, there is no life. This reframes the meaning of destruction. Fire seems like annihilation because it rapidly increases entropy. But entropy increase is universal. It is happening in your bloodstream right now at a slower rate. The key difference is speed and localization. A campfire is obvious because the entropy jump is dramatic and luminous. Rusting iron is subtle because it occurs slowly. Yet both are oxidative processes. Both are downhill transitions in energy. Another layer of depth emerges when we ask what heat actually is at the quantum level. Heat is not a substance. It is not a fluid, though early scientists once believed in a caloric fluid. Heat is microscopic motion. When bonds form and release energy, that energy becomes vibrational motion of atoms and rotational motion of molecules. Those motions propagate through collisions. The hotter something is, the more vigorously its particles move. In a flame, molecular fragments vibrate so violently that electrons are excited into higher energy states. When they relax, photons are emitted. The color depends on the exact energy differences between those quantum levels. Sodium impurities emit bright yellow light because of very specific electron transitions. Even a small trace can dominate a flame's color. Feynman emphasized that temperature and entropy are not mystical drives, but statistical consequences of vast numbers. A flame contains trillions upon trillions of particles. Each follows quantum mechanical rules precisely. Yet the collective behavior becomes overwhelmingly predictable in one direction. Reverse burning is not forbidden. It is simply so improbable that it never happens. Time's arrow emerges because large systems amplify probability asymmetry. And here is the unsettling thought. The laws themselves do not insist that entropy increase. They allow both directions. The increase is a consequence of the universe starting in a low entropy condition. If the universe had begun in equilibrium, there would be no flames, no life, no stars. The very existence of fire is evidence that cosmology and thermodynamics are connected. When you watch a candle flicker, you are seeing the aftershock of the Big Bang. You are seeing the universe still moving away from its original order. There is another subtlety. While microscopic laws are mostly time-symmetric, there are tiny asymmetries in certain particle interactions involving the weak force. These violations are real, but far too small to account for everyday thermodynamic irreversibility. The irreversibility in fire is overwhelmingly statistical. That fact carries philosophical weight. It means that many macroscopic certainties are not absolute necessities, but near impossibilities reversed by odds so extreme they might as well be laws. When you feel heat from a flame on your skin, energy is flowing into you from the region of higher temperature to lower temperature. That direction is not chosen arbitrarily. It maximizes the number of accessible microscopic configurations. If heat flowed from cold to hot spontaneously, entropy would decrease. Such events are not strictly impossible in tiny systems. In very small collections of particles, temporary entropy decreases can occur due to random fluctuations. But in a macroscopic fire, fluctuations of that magnitude are vanishingly rare. So fire teaches a profound lesson. Reality at the deepest level is reversible and symmetrical. Reality at our scale is overwhelmingly irreversible. The flame exists at the boundary between these truths. Beneath it lies quantum electrodynamics, time-symmetric and elegant. Above it lies thermodynamics, statistical and directional. The burning log bridges microscopic reversibility and macroscopic inevitability. If you stand before a bonfire at night, you are witnessing matter converting stored chemical potential into radiant energy, while simultaneously increasing entropy and reinforcing the arrow of time. The crackling sound comes from expanding gases escaping the structure of wood. The rising plume carries ash and hot air upward. The light radiates outward at the speed of light, dispersing into darkness. Every aspect of that scene embodies the statistical direction of the cosmos. If the continents were different, there would be no flame. We have followed fire from chemistry into thermodynamics, and from thermodynamics into the arrow of time itself. Now we must go deeper than combustion, deeper than entropy, deeper even than atoms. Because the final shock hidden inside the question, why does fire burn, is this: the universe did not have to allow it. Flame is not guaranteed by logic. It is permitted by the precise strengths of the fundamental forces in the exact structure of quantum mechanics. If those numbers were slightly different, no one would ignite, no oxygen would bond as it does, and the night sky would never glow from a campfire or a star. When Richard Feynman spoke about the laws of physics, he often emphasized something both exhilarating and unsettling. The constants of nature simply are what they are: the electric charge of the electron, the mass of the proton, the strength of the electromagnetic force. These numbers are not derived from deeper necessity in the standard model as we currently understand it. They are measured, and yet the entire drama of chemistry depends on them. Fire exists because electromagnetism has exactly the strength it does. Electromagnetism binds electrons to nuclei and atoms to atoms. If the electromagnetic force were significantly weaker, electrons would be loosely bound. Chemical bonds would be fragile. Molecules like oxygen and cellulose might not remain stable long enough for complex reactions to occur in a controlled way. If the force were significantly stronger, electrons would cling too tightly. Reactions that release energy by rearranging bonds might require enormous energy just to begin. Combustion as we know it might be impossible. Fire depends on a balanced bond strong enough to store energy, yet not so strong that rearrangement cannot occur. The energy released in combustion comes from the difference in bond energies between reactants and products. Carbon and hydrogen bound in wood sit in one configuration of electromagnetic potential energy. Carbon dioxide and water represent a lower one. The difference emerges as heat and light. But bond energies are ultimately determined by quantum electrodynamics and the value of the fine structure constant, a dimensionless number that characterizes the strength of electromagnetic interaction. Its approximate value is about 1/100. 37 change that value slightly and chemistry transforms radically. The periodic table would reorganize, the geometry of molecules would shift. The conditions that make oxygen reactive in just the right way for fire might vanish. There is also the question of oxygen itself. Oxygen exists because nuclear fusion inside stars forges it from lighter nuclei. The production of carbon and oxygen in stars depends delicately on nuclear resonance levels. If those energy levels were slightly different, stars might produce far less carbon or oxygen. Without carbon, there is no organic chemistry as we know it. Without oxygen in planetary atmospheres, there is no rapid oxidation. Fire on Earth became possible only after photosynthetic organisms filled the atmosphere with oxygen over billions of years.
Before that, lightning may have ignited methane or other gases, but the world did not burn as forests burn today.
Let's consider the chain of dependencies. The Big Bang sets initial conditions. Gravity pulls matter into stars. Nuclear fusion creates heavy elements. Supernovae scatter those elements into interstellar space. Planets condense from that enriched material. Life arises, evolving photosynthesis. Oxygen accumulates. Wood grows, capturing sunlight in chemical bonds. Then a spark ignites those bonds, releasing light once again. Remove one link in that chain, and the flame disappears. Fire is not primitive. It is a late and fragile achievement of cosmic evolution. Feynman would likely caution us not to rush toward mystical interpretations of this apparent fine-tuning. Physics seeks deeper explanations. Some theories suggest that constants may vary across a multiverse landscape. Others search for underlying principles that fix these numbers uniquely. But regardless of interpretation, it remains true that chemistry depends sensitively on the values nature has chosen. Fire exists within a narrow range of possibilities. Even temperature scales matter. Combustion requires activation energy. Bonds must first be broken before new, stronger ones can form. That initial input may come from a spark or friction. The very possibility of activation energy barriers depends on quantum mechanics. Electrons occupy discrete energy levels. Potential energy surfaces define valleys and hills in configuration space. Reactions occur when systems climb small hills to roll down steeper slopes. Without such energy landscapes, reactions would either never occur or happen uncontrollably. The stability of matter alongside the possibility of transformation relies on quantum structure. We can also ask why photons carry energy in discrete quanta. When excited atoms in a flame emit light, they release energy in packets determined by Planck's constant. That constant sets the scale of quantum effects. If Planck's constant were dramatically different, atomic sizes and energy levels would shift. Flame colors would differ, or perhaps no visible light would be emitted at all. Incandescence depends on black body radiation, which itself depends on quantum physics. The glow of hot soot particles in a candle flame is the result of quantized electromagnetic modes radiating energy. And what about gravity? Gravity shapes convection in flames. On Earth, hot gases rise because gravity creates buoyant flow. That flow feeds oxygen into the reaction and carries hot products away. In microgravity, flames become spherical and cooler, often blue and faint. If gravity were stronger, convection would be more vigorous. If weaker, flames would behave differently. While gravity does not determine the chemical possibility of combustion, it shapes its visible character. The teardrop flame we associate with fire is partly a gravitational artifact. The deeper we look, the more fire seems less like a simple everyday phenomenon and more like a convergence point of fundamental principles. Quantum electrodynamics defines bond energies. Statistical mechanics defines entropy. Cosmology sets initial conditions. Stellar nucleosynthesis creates elements. Biology generates oxygen. Planetary conditions allow accumulation of fuel. All of that stands behind the strike of a match. There's another profound angle. Fire is an equilibrium phenomenon. It exists only when energy flows through a system. A flame persists because chemical energy continuously converts into heat and radiation. Once the gradient disappears, the flame vanishes. Non-equilibrium thermodynamics describes such structures as dissipative systems. They maintain organization by exporting entropy. A hurricane exists because temperature differences between ocean and atmosphere drive circulation. A flame exists because bond energy differences drive chemical flux. Life itself is a far more complex dissipative structure. This perspective dissolves the rigid boundary between inanimate and animate processes. Fire metabolizes fuel. It consumes oxygen. It produces waste. It even reproduces in a limited sense, spreading from one region of fuel to another. Yet it lacks internal regulation and information storage. Life adds those layers atop chemical burning. At a molecular level, your cells conduct oxidation reactions similar to those in a flame, but carefully controlled through enzymatic pathways. Instead of erupting as heat and light, the energy is channeled into ATP molecules in cellular work. The boundary between flame and metabolism is not absolute. Both are energy release guided by quantum chemistry. If we push further still, we encounter a question that physics has not yet answered. Why does anything exist rather than nothing? Fire presupposes atoms, forces, space, and time. It presupposes that the vacuum permits fields to exist and interact. In quantum field theory, even empty space seethes with fluctuations. Virtual particles appear and vanish. The vacuum has structure. The laws governing that structure permit stable matter. Those laws also permit instability when favorable rearrangements exist. Combustion is one manifestation of that permitted instability.
Feynman once remarked that the joy of discovering how things work does not diminish the beauty of phenomena. Knowing that flames are electromagnetic interactions does not make them less mesmerizing. In fact, it makes them more astonishing. The orange glow is not magic spirit, but the collective radiation of excited sodium atoms and incandescent carbon particles. The crackle is water vapor flashing into steam and bursting through cellulose fibers. The upward drift is buoyant flow defined by gravity and fluid dynamics. Behind the dance is mathematics, probability, and field theory.
When we ask why fire burns, we are really asking why the universe contains energy differences, why it began in low entropy, why electromagnetic forces have their precise value, why carbon and oxygen exist, why quantum mechanics structures energy into discrete levels, and why thermodynamics drives systems toward probable states. Fire is a window into the architecture of reality. Now consider something quietly extraordinary. Billions of years from now, stars will exhaust their fuel. New heavy elements will no longer form. Galaxies will drift apart. Energy gradients will diminish. In the distant future, there may be no wood, no oxygen-rich atmospheres, no chemical flames. The cosmic arrow of time will approach thermal equilibrium. Fire, as we know it, is temporary. It exists only in a universe far from equilibrium. Every flame is a fleeting chapter in cosmic history. That realization should not depress us. It should sharpen our sense of wonder. The match you strike tonight participates in a story that began in stellar cores and will end in cosmic silence. The light you see left atomic transitions defined by constants woven into the fabric of space. The heat you feel is molecular motion born from quantum electrodynamics. The direction it spreads defines your sense of past and future. Fire is not just burning wood. It is the universe expressing its laws. So if someone asks why fire burns, the shortest honest answer is this: because the laws of physics allow matter to rearrange into lower energy states while increasing entropy in a universe that began in extraordinary order. But the longer answer, the one Feynman would smile at, is that the flame is a visible signature of quantum fields, statistical inevitability, cosmic history, and fundamental constants converging for a moment in space and time. And once you truly see that, fire does not merely warm your hands. It dismantles the illusion that reality is simple. It reveals that even the smallest everyday phenomenon is anchored in the deepest architecture of existence.